How are you all doing this morning?
Doing okay. How are you?
Today we're going to be talking some more about op amps. A little bit later on in the class, I'm going to be introducing some very commonly used op amp topologies. But before we get into that, I'd like to work a few more example problems that are in line with what you might see on your exam. So for our first circuit that we are going to analyze, it's going to be a little different than anything that we've done to this point, I believe, but it should absolutely be analyzable using the method that we've talked about. All right, so this is our circuit of interest. And this guy looks to be a bit complicated, but in truth, it really won't be. So before we get into our analysis specifically, I'd like to remind you guys of the rules. So rule number 1 is there can be no potential difference between the input terminals So if I define this voltage to be V plus, the voltage present at the non-inverting input terminal, and this voltage to be V minus, the voltage present at the inverting input terminal, then rule 1 simply means that V plus has to be equal to V minus. And then rule number 2 states that no current can flow into or out of the input terminals, which means that if I call this current I plus, it has to be 0 amps, and this current I minus also has to be 0 amps. All right, so with a refresher on the rules, who can tell me what our first step of analyzing an op-amp circuit should be? Who remembers from last Thursday?
You find the voltage at the non-inverting input.
Exactly right. Find the voltage V plus, where we'll have to apply rule 2 as needed. So how would we determine that voltage V plus in this particular circuit? Any thoughts? All right, let me ask you guys a question. Do you believe that there is a current that is leaving our 1-volt source and is going to flow through the 20 kilo ohm resistor? Is there any reason why we wouldn't have a current that I've drawn in blue?
V plus be just minus that 1 volt because we only have technically 1 voltage source connected to that terminal.
I disagree. So if V plus were 1 volt, that would mean that that current that I've drawn in blue would have to be 0 amps. And I would argue that we have no reason to assume that, right? So let's assume that there is some current that is leaving the positive polarity terminal of our voltage source, because to me, I can't think of a reason to justify why we don't have any, all right? That current that leaves our 1-volt source is going to flow into the 20 kilo ohm resistor, and then it's going to flow over here to this node. What is going to happen to that current, whatever it happens to be, when it hits that node? Is it going to flow down through the 80 kilo ohm resistor? Is it going to flow right into the non-inverting input terminal, or is it going to be some combination?
It's going to flow right.
So I heard one person say that it's going to flow right, and I had another person begin to speak, I think.
Yeah, I was gonna say it was gonna go down through your 80 kilo ohm resistor because you can. According to rule 2, you can't have a current flowing through that terminal right there.
Exactly right. So all of that current in blue is going to flow down through the 80 kilo ohm resistor. And then according to Kirchhoff's current law, then it must all flow this way. So we're just going to have this current in blue kind of flowing in a circular loop. So from the perspective of that current, that voltage source, just we have a 1-volt source that sees 2 resistors in parallel. Or excuse me, 2 resistors in series, I'm sorry. And we are trying to find the voltage present at the non-inverting input node, which is the exact same as the voltage drop over the 80 kilo ohm resistor. This voltage is also V plus because by definition, our voltage V plus is between this node and our reference node. So understanding that, what is our voltage V plus? Any thoughts?
We need to find Req and then use Ohm's law to get the current.
We can.
Say, could you, since they're in series, we know they're gonna have the same current passing through them, so could you just do your voltage divided by your resistance, and then I got 1 volt divided by 20 kilo ohms is 0.05 milliamps, and then multiply that by 80 kilo ohms to get a voltage.
All right, so you're both close. The first suggestion was a little bit better. So, and the reason why I say that, so if we assume, so the second person who spoke said that we would divide 1 volt by 20 kilo ohms to get our current. Now, the problem with that is assuming that there is exactly a 1 volt drop over the 20 kilo ohm resistor, meaning that we were assuming that that node is ground, and we have no reason to assume that that node is ground. We don't know that 1 volt drops over the 20 kilo ohm resistor. We know instead that there is 1 volt drop over the 20 kilo ohm resistor in series with the 80 kilo ohm resistor. So that first suggestion of taking 1 volt and dividing it by the total resistance, giving us the current, and then multiplying it by 80 kilo ohms is more correct. I would argue that we could treat this guy as a voltage divider circuit, because we know that none of the current can branch off and flow into the input terminal. We have a 1 volt source that sees 2 resistors in series, and we just want to know the voltage drop over one of those resistors. So this is a perfect time to apply voltage division. So using the voltage division method, we would have 1 volt is going to be multiplied by 80 kilo ohms over 20 kilo ohms plus 80 kilo ohms should be 0.8 volts. So that's voltage division. Using the other way that was suggested, I'm just going to call this current IS. IS would be 1 volt divided by 20 kilo ohms plus 80 kilo ohms. So 1 over 100 kilo ohms would give us, I think that's 10 milliamps. Let me double check. Yeah. 10 microamps. And so therefore, V plus would be 80 kilo ohms times 10 microamps would be 0.8 volts. So either way works. We get the exact same result either way. But in my opinion, recognizing that that input stage there is a voltage divider gets us to our result a little bit quicker. So any questions about what we have done, what we've done thus far? All right. What is step number 2 in analyzing an op-amp circuit?
Saying that V plus is equal to V minus.
Right, so effectively just applying rule number 1. So find V minus, apply rule number 1. So we know that V minus is exactly equal to V plus is exactly equal to 0.8 volts. So just to be clear, I'm going to say that we have 0.8 volts here and 0.8 volts here. What is rule number 3? excuse me, not rule number 3, step number 3.
Apply KCL to figure out V out.
All right, so apply KCL where?
On the inverting input.
Exactly right, the inverting input terminal. So apply KCL at the inverting input with rule number 2 as needed. All right, so our inverting input terminal node is here. So let me use orange. So what we're going to do is we're going to say that we have this current flowing down through the 1 kilo ohm resistor, this current flowing to the right through the 5 kilo ohm resistor, and we add them together and set it equal to 0 because we know that the current that's flowing up has to be 0 because it's a current that's trying to flow into one of the input terminals. So what is the current flowing down through the 1 kilo ohm resistor? Or how do I get it?
0.8 volts over 1 kilo ohm.
All right, 0.8 volts divided by 1 kilo ohm. Perfect. What is the current flowing to the right? Through the 5 kilo ohm resistor.
That would just be 0.8 or divided by 5 kilo ohms. Or not 0.8 minus V out divided by 5 kilo ohms.
Perfect. 0.8 volts minus V out divided by 5 kilo ohms is equal to 0. And this gives us enough information. So tell me when you've got an answer.
4.8 volts.
4.8 volts. Absolutely right. All right. Any questions about this problem? This one was a little tricky, a little tougher than what we've been seeing, at least in my opinion.
How did you know the directions for the currents when looking at the non-inverting terminal?
So it doesn't matter. And I'm not saying like, what I'm saying is the directions that I assumed are literally inconsequential, right? I am doing this as if I'm working it as a nodal analysis problem. So I'm saying all of the currents are leaving that node, but I could have set it up to where the currents flowing in is equal to the current flowing out, or all of the currents flowing in are equal to 0. Whatever convention that I choose is perfectly fine. And so whatever direction for those currents that I choose, I will still get the same answer if I apply KCL correctly. So just as a quick proof, let's change the direction on that guy. Let's work it, this guy and this guy. We'll do it over here as a quick aside, right? So the current flowing down doesn't change. That would be 0.8 volts divided by 1 kilo ohm. And the would be equal to, so that's the current leaving the node. So the current leaving the node has to be equal to the current flowing in, where the current flowing in is V out minus 0.8 volts over 5 kilo ohms. And if we solve this guy, we still find that V out is equal to 4.8 volts. We could do it with the opposite sign directions, or excuse me, the opposite directions for the currents. It doesn't matter how we do it as long as we're applying, or what, it does not matter what directions that we assume for any of the currents, as long as we are applying Kirchhoff's current law correctly.
How did you know to say that the voltage drop over the 80 kilo ohm resistor was the same as our voltage at that non-inverting input?
Fantastic question. So the voltage at our non-inverting input node is a nodal voltage, meaning that it is measured with respect to ground. So sorry, that's the wrong thing. This node right here that I've just drawn an arrow at is the non-inverting input terminal, or how it's connected to that resistor network, correct? Because it's just a short over to the non-inverting input denoted by the plus sign.
Yeah.
All right. Ground is this guy down here. So V plus, by definition, is the potential difference between this point and this point, which is the exact same thing as the voltage drop over the 80 kilo ohm resistor.
Okay, I got it now.
Yeah. The voltage present at the inverting input terminal is the exact same thing as the voltage drop over the 1 kilo ohm resistor. But we always find the voltage at the non-inverting input terminal first, and then use that to be able to solve for V out. If we didn't figure out what the voltage at the non-inverting input terminal was first, we actually couldn't solve for V out, because V out is always going to wind up in an equation with V minus. All right, let's mess around with something else. Let's say that I have the following circuit. All right, so our goal here is to determine the value of the resistor R such that the power absorbed by our 10 kilo ohm resistor is equal to 150 milliwatts. So there's actually something pretty important here that I'm not entirely sure that we've discussed yet. So let's analyze this circuit like we were trying to find that quantity V out. Okay. How would we go about doing that? If we were trying to find V out, we didn't care, like, let's say that R had some specific value and we just wanted to know what V out was. So we were working this like any other circuit that we've analyzed to this point. What would we do?
Solve for V plus and V minus first.
Okay, so what is V plus?
5 volts.
What is V minus?
5 volts.
What is step 3?
KCL at the non-inverting input terminal.
Okay, so what's that equation going to look like? To be clear here, we're going to be adding this current plus this current and setting them equal to 0. So what's the current flowing down through R?
This should be 5 volts over that R value that we don't know yet. So 5 over R.
So 5 volts over R. Okay, what's the current flowing to the right?
5 volts over 1 kilo ohm.
So that is assuming that V out is equal to 0. Can we safely make that assumption?
No.
No, not yet.
Right. So take another stab at it.
5 volts minus V out over 1 kilo ohm.
5 volts minus V out over 1 kilo ohm. That is correct. Set this equal to 0. So we don't know what R is and we don't know what V out is, but I would argue that we have enough information to figure out what V out is. But before we do that, let me ask you guys a question, and I hope it's a pretty simple one. Would the value, let's say that R had a constant value. Let's say that R was 1 kilo ohm as well, just for the sake of argument, okay? Would the value of V out change if that 10 kilo ohm resistor were, say, a 20 kilo ohm resistor?
If we knew the value of R, then no, it shouldn't.
Exactly. So it doesn't matter what our load resistor is there that's connected to our output. Our output voltage is effectively independent of what we have this guy connected to, other than a short circuit, which would force it to be 0. So when we're given the power here, we know then that we can relate that the power absorbed by that 10 kilo ohm resistor to the voltage drop over the 10 kilo ohm resistor, which is exactly the output voltage of our op amp. Okay, so we know that V out, actually, let me start differently. We know that P out, or the power being absorbed by the 10 kilo ohm resistor, I guess I should write it the same way. Sorry, I'm erasing so much stuff. P 10 kilo ohms equal to V out squared divided by 10 kilo ohms. And it could potentially also be, let's call this guy right here, I out squared times 10 kilo ohms. If we wanted to solve this circuit, hopefully it's obvious, we would wind up using this relationship. As a matter of fact, we will literally never use this relationship, and it's because we don't know how the current that is being output by the op amp behaves other than without knowing what the voltage present at the output is. okay? None of our relationships have anything to do with the output current or the current leaving the output terminal of an op amp, okay? So we can never use this guy over here on the right. It's technically correct, but we would have to know V out in order to determine I out. So with that in mind, how do I solve for V out?
150 is equal to V out squared over 10 kilo ohms, solve for V out.
Yeah, so V out would be the square root of P 10 kilo ohms times 10 kilo ohms would give me 38.730 volts. Now, technically, it could also be negative 38.730 volts, right? When we take the square root, it could be plus or minus. But in this case, we know that it is definitely going to be positive 38.730 volts because we are applying a positive voltage to the non-inverting input terminal, okay? So you guys may not have recognized this yet, and it's going to be something that we talk about in just a few minutes, but whenever we apply a voltage to the non-inverting input terminal, our output voltage has always been positive. And whenever we have applied a voltage at the inverting input terminal through some resistor network, our output has always been negative. It's because the non-inverting input terminal amplifies positive signals. So if we get positive in, we get positive out. The inverting input terminal means that if we put positive in, we get negative out. If we put negative in, we get positive out. It inverts or changes the polarity of the input signal. So now that we know what V out is, somebody tell me what the value of R needs to be.
Uh, 0.148 kilo ohms.
0.148 kilo ohms. All right, so 0.148 kilo ohms, which I got to be 148.276 ohms. Great. So that one was another one. Honestly, I would feel that that one was too difficult to put on the exam. Let's do one more, and then we'll move along to today's actual topic.
Can you scroll back up for just 1 second?
Absolutely.
Thank you.
And if there are any questions about this one, by the way, please ask.
Thank you.
Alrighty. All right, so this guy is going to be a little bit of a doozy. And I say that meaning that it's going to look very complicated, but we can still use those 3 simple steps and solve this guy. We're just going to have to do a little bit of finagling here. So this would be type of problem that I might ask on your exam if I were in a very, very foul mood when I created the test, which I can't say that I've ever asked one this difficult, and in all honesty, it's not that difficult. All right. So this is about the meanest single op-amp circuit I can think of. We can solve it using the exact same methodology that we have been doing. We just need to think about a couple of things here. All right. So let's start with step number 1. What is the voltage present at the non-inverting input terminal? Anybody have any thoughts on how we might determine it?
It looks to me like 0 volts, but I'm not sure.
Could you explain your reasoning, please?
So you have the 2 milliamp current source and the 3 kilo ohms both connected to ground and going into the positive. So if they're both grounded on like one side, then that means 0 volts is going into the positive terminal. But,
I would argue we know that 2 milliamps is flowing up and leaving this current source. None of it can branch off and flow into the positive polarity terminal. So all of it must flow down through the 3 kilo ohm resistor into ground and return like so. So our voltage here, V plus, is the exact same thing as the voltage drop over our 3 kilo ohm resistor. Does that make sense?
yes.
So knowing that all of that 2 milliamps of current has to flow through the 3 kilo ohm resistor because there's no other path for the current to take, what should the voltage drop at the non-inverting input terminal be?
6 volts.
6 volts. Perfect. 2 milliamps times 3 kilo ohms is equal to 6 volts. Absolutely correct. Does everybody understand why that works that way? It's effectively just rule number 2. No current can branch off, so all the current has to flow in that little loop, giving us a voltage V plus is equal to 6 volts. Step number 2, we find V minus, which is the voltage right here. What is it going to be?
6 volts.
6 volts, because it has to be the exact same thing as V plus. All right, here comes step 3. So I have drawn the circuit in a way to make this intentionally difficult. So I would like for one of you guys to tell me what you think the answer is, and then we'll likely pick it apart. So I'll tell you how to check things out. So to be clear, we're looking for that current plus this current and setting them equal to 0.
You have 6 volts, 6 volts minus 3 volts over 10 kilo ohms plus, would you include that 5 kilo ohm resistor in the bottom?
So there isn't a 5 kilo ohm resistor. There is a 500 ohm resistor and a 50 kilo ohm resistor. I'm not sure.
I'm talking about the one on the far left, right up under the 3
Oh,
volts.
okay. So let me, what do you mean by include it?
Would you include that in the Kcl equation? Because technically the current, if we're analyzing the current that's flowing through that 10 kilo ohm, wouldn't that current have to flow through that 5 kilo ohm resistor as well before it hits ground?
Absolutely right. So this would look like 10 kilo ohm plus 5 kilo ohm. All right, so you caught something that very few students catch. What I would argue, now your methodology is perfectly correct. What I would argue is the 10 kilo ohm resistor and the 5 kilo ohm resistor are in series. So what you could do is simply change their order like that, and it becomes much more obvious that it should be 6 volts minus 3 volts over that total series resistance of 15 kilo ohms. But you caught it drawn the goofy way, so you're doing very, very well. All right, so what about the current directed to the right?
That should just be 6 volts minus V out over 17 kilo ohms plus 500.
Exactly right.
You had to convert kilo ohms and do all that, but
Yeah, that's not that big of a deal. So set this equal to 0. So just to be clear here, this would simplify to 6 volts minus 3 volts over 15 kilo ohms plus 6 volts minus V out over 17.5 kilo ohms. Absolutely correct. That is a fantastic job. Most people neglect this guy here and that guy there. So you did a wonderful job. So if we solve this guy, what will V out be?
9.5 volts.
9.5.
All right, 9.5 volts. So does the fact that there's a 50 kilo ohm resistor between this node and where we're measuring V out change your answer in any way? Effectively, what I am suggesting is that you are assuming that our voltage V out occurs at this node here in the middle that I'm making real big, when V out is actually defined to be this guy. Does that change your answer?
Yeah, I don't know about that one.
All right. Let me ask you a different question. What is the value of the current flowing through the 50 kilo ohm resistor? Any thoughts? From anybody?
V out over 25 kilo ohms. Oh, no, over 50 kilo ohms.
All right. So when you say V out, you mean this guy right here. I'm going to call this guy V out prime so there's not as much confusion. So are you meaning that
Yes.
V out prime? Okay, so V out prime over 50 kilo ohms. That would make the assumption that this node right here is grounded. but it isn't because there's a big open circuit terminal, right? So if that current I50K were V out prime divided by 50 kiloohms, that would be saying that this V out is equal to 0 volts. And I disagree wholeheartedly. So let me ask you a slightly different question. How much current can flow through an open circuit?
Unlimited.
An unlimited amount. All right. So to be clear, we have an open circuit set of terminals like so. You are saying that the amount of current that can flow through it is unlimited. What is the resistance of an open circuit?
Zero ohms.
Okay, so you have something confused, which is exactly what I thought you had confused. You are confusing an open circuit with a short circuit, okay? An open circuit has an infinite amount of resistance, okay? And a short circuit has 0 resistance. So for an open circuit, no current can flow through, and the voltage can be whatever it needs to. And for a short circuit, no voltage drop can occur, and the current can be whatever it needs to. So think about it this way. Let's say that you have an outlet on your wall, right? A receptacle that's going to look something like this. We have a large opening over here, and then typically speaking, a smaller opening. They could be the same size. It just depends on whether the polarity of things matter. Oops. And then you might also see something that looks like that guy on the bottom. That's where the ground prong goes. That has nothing to do with what we're talking about right now, okay? This is the positive polarity terminal of your outlet. And this is the negative polarity terminal of your outlet. And if nothing is plugged in, no current will flow between those 2 points, right? It requires us completing the circuit in order for any current to be able to flow through there. Otherwise, your electricity bill would always be, if you had nothing plugged up, your electricity bill would be higher than if you had everything plugged up, because you'd always have current flowing until you did something, okay? So just to reiterate, for an open circuit, I is equal to 0. V is whatever it happens to be based on the rest of the circuit. For a short circuit, here's an open circuit, here's a short circuit. V is equal to 0. And the current is whatever it needs to be. So let me define things here. Here's V, here's I, here's V, here's I. Okay, so if we have an open circuit in the circuit, which we absolutely do, right here, that means that I50K, the current flowing through the 50 kilo ohm resistor, must be 0. Since the current flowing through the 50 kilo ohm resistor must be 0, what is the voltage drop over the 50 kilo ohm resistor according to Ohm's law?
0.
0 volts. That is why V out prime, the voltage at that node, and V out that I've just circled in orange are the same thing, because Since no current can flow through the 50 kilo ohm resistor, then a simple application of Kirchhoff's voltage law would tell us that those are the exact same things. I could break that by putting a resistor here, right? So if I put a 50 kilo ohm resistor like so, and now called this guy V out, we could use voltage division to figure out what the relationship is between this voltage and this guy. Is that clear, or did I just confuse everybody?
Moderately confused.
Okay. So I want to go back through the analysis bit right here to explain what I'm talking about. All right. So when we wrote our Kcl equation, these guys right here, that we had 6 volts, which was the voltage here, minus, and then it was said minus V out. All right. Well, V out, let me redraw this thing how it was. So it's not. V out is technically this guy right here. So what I believe Mr. Gray meant was the voltage present at the output terminal, which is the voltage right here. So these should technically be V out prime. All right. We can say that V out is exactly equal to V out prime because we know that I-50 is 0. If there were not an open circuit over which we were measuring V out, if there were a resistor instead, then the relationship between V out and V out prime would have to change because that current I-50 is no longer 0. Did that explanation make any sense?
So V out equals V prime because it's an open circuit.
Exactly right. So V out is equal to V prime because it's an open circuit. So effectively, ignoring the op amp entirely, okay? The op amp is generating a voltage. Let's just call it V prime. Then we had some resistor. And we wanted to know what this voltage is. They must be identical because this current is 0, which means this voltage, VR, is 0, which was how the circuit was originally set up, right? So a simple Kirchhoff's voltage law would tell us that we have negative V prime plus R times our current, which is 0 amps, plus V out is equal to 0, which gives us V plus is equal to V out. That is what our original circuit looked like. Now, we have that voltage V plus. We have some resistor R. And then we have another resistor. Let's just call it R2 for the sake of argument. We are trying to find V out. We are going to get a different answer here because this current I does not equal to 0 amps. That's all I was trying to illustrate. Okay. Let's talk about some common op-amp circuits. Circuit number 1. I'm going to call this resistor here R2. We're going to solve this guy generically. Let's call this guy right here 1. And let's call this guy Vn. And then we'll ground this guy here. So our goal is to analyze this circuit and to develop a relationship between V out and Vn. Okay, so we're looking for an input-output relationship for this particular system. So what is the voltage present at the non-inverting input terminal?
Vn.
It would just be VN.
Absolutely correct. What is the voltage present at the inverting input terminal?
It should be Vn as well.
Exactly right, simply Vn. So what is my Kcl equation at my inverting input terminal going to look like?
Should be Vn over R1 plus Vn minus V out all over R2.
All right, and so with a little bit of algebra, I could rearrange this, and I would find that V out is equal to negative, so actually, I'm sorry, that's not correct. 1 plus R2 over R1 multiplied by Vn. So this is our input-output relationship for this particular circuit. I'm going to put a box around it. I'm going to define something else here real quick. The concept of what's called the voltage gain. So the voltage gain for an amplifier circuit is simply the ratio of the output voltage divided by the input voltage, which in this case will simply be that resistor ratio, 1 plus R2 over R1. Put a box around this guy again. this guy too. So let's take a look at this voltage gain real quick. It is 1 plus R2 over R1. So that means that our voltage will, A, always be positive. So if we put a positive input voltage in, we get a positive input voltage out. And B, it will always be 1 or greater, right? So if R2 were a short circuit, this guy would give us a gain of exactly 1. And if R2 has a resistance larger than 0, then our voltage gain just gets larger and larger and larger, right? Now you may be asking yourself, how is this representation at all helpful? Okay. And so what I would like to do is circle back around to the very first problem that we looked at. And I'll draw it again. Real quick down here. We had something like this. Positive here, negative here. I think this was a 5 kilo ohm resistor. I believe this was a 1 kilo ohm resistor. Actually, there was a resistor here. I want to say that this was 1 volt, this was 20 kilo ohms, this was 80 kilo ohms, and these guys were ground. Might not have been drawn exactly like that, but it was pretty close. All right. Trying to think of how I can get both of these things on the page at the same time. Let me figure out how to zoom out. Okay. So everything that I'm about to enclose in this box is exactly what I've drawn with circuit number 1. Okay, it looks different, but if we pay attention here, there is a feedback resistor between the inverting input terminal and the output terminal. So 5 kilo ohms is effectively R2. And there is a resistor between the inverting input terminal and ground. So that means this 1 kilo ohm resistor here is acting like R1. So as soon as we figure out what this voltage is, V plus, which we found to be 0.8 volts using voltage division, we could then plug that in to our equation and find that V out in this case has to be 0.8 volts times 1 plus 5 kilo ohms over 1 kilo ohm will be equal to 4.8 volts without having to do any circuit analysis whatsoever if we are able to recognize that what I have circled in this green box is circuit number 1. Okay, that's what these common op-amp topologies are for. Once we can recognize what they are, we know that they're always going to behave in this certain way, and they're always going to have this particular input and output relationship. We no longer have to do any circuit analysis whatsoever. It's simply, we know what the input is, we know what the voltage gain is, so the input multiplied by the gain gives us the output. All right, let me circle back around here real quick. So Now I'd like to show you how you might see this circuit and it make no difference whatsoever. So you could see some resistor here. I'm just going to call it R3. Would having some non-zero resistance for R3 change our relationship for this circuit at all? No, but with a question mark. So I will say no, but with an exclamation point. All right. Sarah,
Yes.
what is that current in red? What does it have to be?
Oh, it has to equal 0 because it's going into the input.
Right, which means the voltage drop over that resistor R3 has to be 0.
Okay,
So if
okay.
there is a resistor placed between the input voltage source and the non-inverting input terminal, it doesn't actually do anything as far as we are concerned. There is a very specific reason to do it, but the overwhelming majority of you will not be taking analog electronics too, and so it's completely unimportant for you to understand why that might be there. For the intents and purposes of our analysis, that resistor R3 does nothing. Another place you might see a resistor I'll try to draw the useless ones in pink, would be some load resistor. So I'm just going to call this guy RL. If we have some resistor here connected between the output terminal and ground, does it change any of our relationships whatsoever?
No.
Right. Doesn't have any effect on calculating V plus, obviously, because it's not connected at the inverting input terminal, and it doesn't show up at all, or it would not show up at all in our Kcl equation either. So even if we put a resistor there between the output node and ground, it also doesn't do anything. So we have multiple different ways that we can realize this circuit, but the core that I've drawn in black is the only thing that we would ever have to understand how it works. This guy is what is called a non-inverting amplifier. It is a non-inverting amplifier because if we put in a positive input signal, we get a positive output signal. That is simply that. All right. A question that I've asked on tests before is, how could I increase the voltage gain of a circuit like this? So let me ask you a couple of questions. Will increasing the value of R1 increase the voltage gain of the system?
Like increase VL or what? Like obviously we're increasing R1. Like what do you?
So the voltage gain is this guy right here, right? So if R1 gets larger, does AV get larger?
No.
No, right? The larger that R1 gets while everything else is held constant makes the voltage gain smaller. Decreasing R1. So if we make R1 smaller, does the voltage gain go up?
Yes.
Yeah. Increasing R2. Does that make the voltage gain go up or go down?
Go up.
And finally, decreasing R2. Decreasing R2, since it's in the numerator, should make the voltage gain go down. I might also ask questions about increasing or decreasing the value of R3. That will have no effect whatsoever on the voltage gain. Similarly, increasing or decreasing the value of RL, assuming we don't short circuit the output, will also have no impact on the voltage gain whatsoever, okay? So the gain of this guy is determined entirely, the gain or the input-output relationship of this circuit is determined entirely by the values of resistors R1 and R2. Let's look at another circuit. This is going to be very, very similar. Call this guy between the inverting input and the output R2 again. We're going to measure our output directly at the output terminal, the op amp. This guy VN, this guy R1. So the only difference that I have made between the previous circuit and this one is I have changed the location of ground and where the input signal is applied, right? So before, the input signal was applied here, ground was applied here. We've just swapped those two things, okay? But it is going to change the behavior of this circuit fairly significantly. So let's analyze it. What is V plus going to be?
0 volts.
0 volts.
What is V minus going to be?
0 volt.
Tell me what my Kcl equation at my inverting input node should be.
V in over R1.
All right.
Negative Vn over R1.
I'm going to go with negative Vn. I'm going to adopt the convention that we're taking the currents that are flowing out because that's the way that we have been doing it. But there is absolutely a way to set it up to where we have Vn over R1. But just to be consistent, I'm going to say negative Vn over R1. All right. What's our next term?
Plus V out of R2.
So
Negative
based on
V
the
out over
directions that we have, it'll be negative V out over R2. Right. Sorry. So to be clear, based on our indicated directions, we have the nodal voltage here, which we know to be 0 volts, minus the nodal voltage here, which is Vn divided by R1, which is giving us our first term. So that's 0 minus Vn over R1. For our second term, we have this guy, 0 minus V out divided by R2. And those are specifically based on the directions for which we are assuming current to flow through. So if your currents are flowing in different directions, that's going to change. But I'm trying to make sure that everything is using the same convention. So we could do a little bit of algebra and rearrange this guy, and we would find that V out is equal to negative R2 over R1 times Vn, and our voltage gain is then simply always defined as V out over Vn is just negative R2 over R1. So let's talk about this voltage gain equation here, right? Obviously, we have a negative voltage gain, assuming that our resistor values are positive. We will always have negative voltage gain, which means if we apply a positive input voltage, we get a negative output voltage. And if we apply a negative output voltage, we get a apply a negative input voltage, we get a positive output voltage. So this guy is what is called an inverting amplifier, okay? Now the gain on this guy is interesting because if R2 is greater than R1, our signal gets boosted or amplified. But if R2 is less than R1, our input signal gets attenuated or reduced. It's always going to get inverted, but we have the possibility of making the output signal smaller in magnitude than our input signal, which can be quite useful in some applications. We can never achieve that with our non-inverting amplifier that we previously discussed. It always makes the output signal as large as the input signal or bigger. This guy can actually make it smaller at the expense of changing its sign as well. Okay. If we have some resistor R3 between the non-inverting input terminal and ground, does that change anything?
No, because you can't have a current flowing through that R3.
Exactly right. And similarly, if we apply some load resistance RL, it also changes absolutely nothing because that load resistance doesn't show up in our equations at all. All right. Let's look at two more circuits and then we'll be done. There are actually a couple of more common topologies, but we can't learn about them until we understand how capacitors and inductors work. All right, so give myself some room here. I'm going to call this guy RF now, and you'll see why momentarily. So it is a feedback resistor. I'm going to ground my non-inverting input. So at this point, it looks practically identical to our inverting amplifier. So the change that we're going to make is this guy. Call this guy R1, this guy R2, this guy R3. And I'm going to apply some input voltage VN1 here, an input voltage VN2 here, and an input voltage VN3 here. All right. So I'm going to tell you guys what this one is to begin with. This is what's called a weighted inverting summer or adder. All right. What is V plus in this case?
Zero.
Yep, still 0 volts. So what is V minus?
Zero.
0 volts. Our KCl equation honestly isn't going to be that much more difficult. I just want to be clear about what we're doing here. So we would be taking this current, this current, this current, and this current, and adding them all together. And so I'll go ahead and take care of this for you. It's going to be 0 minus Vn1, so negative Vn1 divided by R1 minus Vn2 divided by R2 minus Vn3 divided by R3 minus Vout divided by RF is equal to 0. And with the slightest smidge of algebra, what we get is that Vout is equal to RF times Vn1 divided by R1 plus Vn2 divided by R2 plus Vn3 divided by R3, and there should be a negative sign right there as well that I forgot. Okay, so this is a weighted inverting summer, and effectively all it is an inverting amplifier with more input signals. Okay, so if we did superposition where we said Vn2 were 0 volts and Vn3 were 0 volts, this guy would behave exactly like the inverting amplifier that we saw a moment ago. And it will behave that way with all of those input signals on one at a time. So it is effectively the exact same thing as an inverting amplifier with all those outputs due to each input signal added together. Okay. So in this way, we can add signals. What happens if R1, R2, and R3 are all the same value? The out is then simply negative RF over, I'm just going to call it R1, times Vn1 plus Vn2 plus Vn3. That would be a simple inverting summer because it no longer has a weight because each input signal is scaled by the exact same amount. Okay. So how many of you have ever driven past a weigh station on your way into or out of a state?
Are you talking about like a weigh station where they weigh the 18-wheelers and stuff?
Exactly right. Yeah.
Yeah, then, yeah.
Yeah, pretty much everybody who's left the interstate or left a state via the interstate has driven by a weigh station. A weigh station uses inverting summers to add up the total weight per axle. It's just got a load cell that is generating each of those little input signals, and then that is converted into a weight using that resistor network, and they're all added together to give you the output of this op-amp circuit as a scaled version of the weight of your 18-wheeler. It's literally this circuit right here, except that Vn1, Vn2, and Vn3, there might be significantly more input voltages, are just generated by a piezoelectric sensor, which effectively measures the weight of each axle. That's it. All right, our last circuit of interest. So this guy was effectively multiple inverting amplifiers tied together into one thing. Our last circuit is going to be an inverting amplifier and a non-inverting amplifier together to create a specific output.
Did that
So
last circuit not have that, like for the first two, you wrote the AV equation, did that circuit not have it, or you shouldn't write
okay,
it?
that is a fantastic question. So this circuit, you can't really characterize the voltage gain on because it is dependent on multiple input signals, right? So we could write one for each input, but that is the exact same voltage gain that we would see for the inverting amplifier. But we can't write a voltage gain equation V out over V in because there are 3 V ins in this particular example. Does that make sense?
I got you. Yeah.
So there is a voltage gain being applied to each of the individual inputs, but there is not a voltage gain for the overall system. All right, circuit number 4. Our last one. This guy is also going to have multiple input signals, so we won't get a voltage gain equation. All right. So I want to point out here that all 4 of these resistors have the exact same value. That's why they're all designated with simply the letter R. So who can tell me what, B plus is?
It should just be VN2.
I disagree.
Oh,
Maybe it'll help if I draw it like this. This current right here is 0 amps. Yes or no?
Yes.
yeah.
All right. So what we have connected to our our non-inverting input terminal here is a voltage divider, just like we had in the first example problem that we worked today. In fact, this guy is extraordinarily similar to the first example problem, except that with some non-zero input signal being applied on the top half here. All right. So based on the fact that this is a voltage divider applied at the the non-inverting input terminal, take another stab at VN2. Take another stab at V plus.
It'll just be VN2 times R over 2R.
Which is
VN over, or yeah, VN2 over R.
almost
Right.
VN2 over 2.
Oh yeah,
Yep, no, not brown. So 1/2 VN2. Everybody understand why that is before we move along here? We know that.
Can you explain that?
Sure. So all of the current that is leaving VN2 will flow through this first resistor R and then flow through the second resistor R and then come back around like so. So what we have is effectively the following circuit. VN2, R, R, and we want to know what this voltage is. So using voltage division, we know that the voltage is going to split up evenly between those two identical resistors. Make sense?
Yeah.
All righty. What is V minus, the voltage present at the inverting input terminal?
1/2 VN2.
Absolutely. Now we write our Kcl equation, right? So we want this guy plus that guy and set them equal to 0. So tell me what that's going to be.
Uh, 1/2 VN2 minus VN1 all over R.
All right.
Plus 1/2 VN2 minus V out all over R.
All right. So what I'm about to do is I'm going to move V out to over R to the right-hand side of the equal sign. So that is going to give me 1/2 VN2 over R minus VN1 over R plus 1/2 VN2 over R is equal to V out over R. Did everybody follow my algebra there?
Yes.
All right. Since we have a common factor of 1 over R in everything, they all cancel each other out, right? So if I multiplied through by R, I would be left with the following equation. V out is equal to 1/2 VN2 plus 1/2 VN2, which is just VN2 minus VN1. So this guy is what's called a differencing amplifier. Because it literally just takes the difference between the two input signals. Now, right now, dealing with DC inputs, this is incredibly boring, right? Because you're just subtracting one voltage from another. But you can use this guy to take the difference in time varying signals, and then it can be extraordinarily useful. Differencing amplifiers are used a lot in radios and stuff like that to be able to discriminate between the message signal and the carrier signal and all that kind of good stuff. All right. I think that is enough out of me for today, and we only have about 10 minutes left of class anyway. So for
What
your
did you call this circuit again? Sorry.
a differencing amplifier, because it
Okay.
just takes the difference VN2 minus VN1. Okay. So we could take the difference and then we could actually feed it into another amplifier and then boost the difference if we wanted to. But cascaded amplifiers are beyond the scope of this class. All right, so with regards to the kind of stuff that you should expect on your exam, circuits like the first one that we analyzed and the circuits like the last one that we analyzed on Thursday are more appropriate as to what you should see. I'm going to be putting up, per you guys' request, several op-amp problems from old tests, and I'm going to group them all together so that you can have lots of practice and all that kind of good stuff, and you'll see the types of stuff that's going on here. I would argue that it is not entirely necessary for you guys in particular to memorize the equations for an inverting op amp versus a non-inverting op amp versus a differencer or anything like that. But you can absolutely use these circuits to not have to go through the 3-step analysis process. So like if you recognize it, then you can use that result. But there is nothing at all wrong with you going through that 3-step process for everything. It isn't until those of you that wind up taking circuits 2 will be dealing with these guys so much that memorizing the different types will actually be of a significant benefit. So for you guys, understanding that they're there is perfectly fine, but just using that 3-step process to solve any circuits is perfectly reasonable. All right, does anybody have any questions regarding any of this material before we wrap things up?
I have a question about the grades for the test. Like I seen that they were in, but what, like, are we going off the percentage or the grade?
So I have it set as out of 105. So I believe it tells you what your grade is out of 105, but I don't think it tells you what the percentage is, if that makes
Okay.
sense.
I was, because it had a grade and then a range from 0 to 105, then it had a percentage right next to that, and I didn't know.
Okay,
what
so
that
ignore
was.
the percentage thing. The
Okay.
one out of 105 is what it should be. So if anybody made over 105, over so like 102 means that you got 102 bonus points, 100% on the test and then 2 bonus points. But a 70 just means that you got a 70 out of 100 for the exam.
Okay, thank you.
Yep. Anything else? Alrighty, I will see you guys on Thursday. Have a good middle of your week, I guess.